Now I will talk about the test which is called as the Wronskian test for the solutions of differential equations. So suppose we have a differential equation in this form: y double prime is equal to some function p of x, y prime plus some function q of x, y is equal to 0. So as you can see, this is a second order equation with the coefficients of y prime and y as two functions of x. So well, these can also include the constant coefficients, and this is a homogeneous equation. So suppose if this equation has two solutions, y1 and y2. Okay, so we know one method for finding that the solutions are independent is that we can take the ratio. There is another method, and that method is called as the Wronskian test. So this Wronskian test is that we can find a algebraic expression or quantity y1 times y2 prime minus y2 times y1 prime. And if we see that if it is not equal to 0, then the solutions are independent. Okay, so this is a very useful test which can be also used for some other derivations as well. Although of course the ratio test is also useful, but in some other derivations we will be using the Wronskian test for the derivation of formulas. So the Wronskian test is it resembles a determinant when we arrange these solutions y1, y2, and their derivatives y1 prime and y2 prime in the form of a determinant. So from the matrices, we know that the determinant of a matrix is for a 2 by 2 matrix is y1 y2 prime minus y2 y1 prime. And similarly, if we have three solutions, so we can find the determinant of their original function, first derivative and second derivative, to find the Wronskian. But of course, in this case, we are only focusing up to only 2 by 2 matrices. So if that Wronskian is not equal to 0, then the solutions will be independent. For the time being, we will be only looking at this application of Wronskian. So as an example, we can test the Wronskian of these two functions. So function 1 is cosine of omega x, function 2 is sine of omega x. So y1 prime will be equal to minus omega sine omega x, and y2 prime will be equal to omega cosine omega x. So we can, if we want to find the Wronskian, then I will multiply y1 with the y2 prime, so it will be omega cosine square x, omega cosine square omega x, and minus y2 y1 prime minus this minus, then 2 times it will come, so it will be plus omega sine square omega x. So we can take omega constant, and then cosine square omega x plus sine square omega x, and we know that sine square x plus cosine square x is equal to 1. Similarly, cosine square omega x plus sine square omega x will be also equal to 1, so it will be equal to omega. So since omega is a value. Okay, so omega is a value which is not equal to 0. Okay, if for example it will be 0, then there are no significant functions over here. So this means that Wronskian is not equal to 0 over here, and then we can say that these two functions are independent. So if these two functions are independent, then there must be some differential equation representing that function. So we can find that differential equation. So since we know that for a homogeneous second order equation, if the characteristic equation has complex conjugate roots, then their solutions are in terms of cosine x and omega sine x. So in those situations, the solution of the characteristic equations are of this form. So if the characteristic equation we represent in terms of lambda, so the solutions are of this form. So alpha plus beta I. Okay. So where a beta term will go with the alpha plus minus beta I. So where beta term will go with the cosine and sine, and alpha term will go with the exponent e. Okay, because the general solution for that equation will be y is equal to a e power alpha x bracket cosine x, cosine cosine beta x plus sine beta x. So in this case only terms of cosine and sine exist, so therefore alpha will be equal to 0 and beta will be equal to, of course, gamma. So the two solutions are gamma 1 will be equal to omega I and gamma 2 will be equal to omega minus omega I. So from here we can form the characteristic equation as lambda 1 minus omega I is equal to 0 and lambda 2 minus omega I plus omega I equal to 0. So we can multiply both the equations together, so it will be here we don't need to put the subscripts because now we are using lambda as variable. So it will be lambda square minus omega I square equal to 0. So lambda square plus omega I square. So I square is minus 1, so it will be minus minus plus, so it will be lambda square plus omega square is equal to 0. So if the characteristic equation is lambda square plus omega square is equal to 0, so the lambda square represents the second derivative y double prime, and omega square term without any lambda will represent the y term. So this will be the differential equation. Okay, so in this way we can reverse the process to find the differential equation from the solutions. In fact, it will be omega square y. Let's take another example. Suppose these two solutions are y1 is equal to c1 e power x and y2 is equal to c2 x e power x. So c1 and c2 are constants. So whether these are unique solutions, so obviously they are unique. But just to find, if you want to find the Wronskian, then we can take the determinant. Okay, just take out ignore those c1 and c2 at the moment. At this moment, x e power x, x e power x. So it will be determinants. The derivative will be e power x. So it will be x e power x and plus e power x. So what will be the Wronskian? E power x times this multiplied x e power x plus e power x minus e power x x e power x. So it will be x e power 2x plus e power 2x minus x e power 2x. So x e power 2x minus x e power 2x cancels, but still e power 2x remain. So this means, which is not equal to 0. So therefore we can safely say that these two are independent solutions. From these two solutions, if we want to find the equation, so we can see that we can recall that this is the situation in the case of the double roots. So the roots in this case for the characteristic equations are m is equal to the general solution is represented by this. So c1 plus c2 x e power alpha x. Okay, so where the alpha is the root of the solution. So alpha in this case is 1. So m is equal to 1 in this case. So m minus 1 is one solution. So it means that m minus 1 square will be also 0. So m square minus 2m plus 1 will be the characteristic equation, and the corresponding differential equation will be minus 2y plus y is equal to 0. Okay, so as another example, we can consider cosine of 5x and sine of 5x. So we can readily see that its characteristic equation will be equal to because these are the lambda values. So the characteristic equation will be equal to m or lambda. We can use, sometimes you can use m, you can either use lambda as well. So m minus m is equal to 5i, or m is equal to minus 5i. Okay, so m minus 5i is equal to 0, or m plus 5i is equal to 0. So if we multiply these two terms, m square minus 5i square, so m square plus 25 is equal to 0. So in this case it will give a differential equation y double prime plus 25y is equal to 0. Okay, so that's all for this topic.